Ladies and gentlemen, good afternoon and welcome to our seminar on predicting injury severity with Bayesian networks and BayesiaLab. Thank you so much for joining us. Let me start off by introducing myself. My name is Stefan Conradi and I'm the managing partner of Bayesian USA. Many of you will already know me from previous webinars. This is part of a new webinar series that we started a few weeks ago. Today's seminar topic is obviously about predicting injury severity. Next week, we will move to a topic where we don't use any data at all. We will talk about probabilistic reasoning under uncertainty with Bayesian networks. That should be quite interesting, and I hope many of you will join us. After that, we will venture into risk management on March 9th. So if you're interested, please make sure to join us and register for these webinars. But let's not talk about what we're going to do today. We are already in the middle of the introduction. I'll tell you a little bit about who we are and what we do. I will address some frequently asked questions and then quickly move into motivation and background. Today, it's all about predicting injury performance with the objective of improving triage performance. And we will talk about what exactly that is. And then most of the afternoon, we want to spend on actually doing the work, to performing the study with BayesiaLab. We will do a few exploratory analysis steps, but then really spend most of our time on predictive modeling. So let me perhaps clarify some nomenclature because the term Bayes will pop up over and over again. Our company is named Bayesian, that's who I work for. Our product that you will see in action, that's BayesiaLab. But all really revolves around the paradigm of Bayesian networks. Bayesian networks were invented by Professor Judea Pearl, who has been teaching and researching at UCLA since 1970. And there's a lot to talk about in the context of this paradigm, the mathematical formalism. Unfortunately, we don't have nearly enough time to go into any detail today. So for that, I would like to refer you to our book that you can download for free on our website. You can also get a hard copy on Amazon. That takes you through some of the theoretical aspects of Bayesian networks and gives you a sense of how they work and Bayesian inference and so on. What I want to share with you today is really how we have taken this mathematical formalism and translated it into a research software, or even more a research workflow, if you will. And here's the most generic version of that BayesiaLab research workflow. It shows how you can build Bayesian networks, and I'll try to use my laser pointer here, either through knowledge modeling. This is what we're going to do next week in our seminar. Today, we will perform machine learning and do knowledge discovery from data. Either way, we can build a Bayesian network, and once we have that Bayesian network, we can use that for analytics, simulation, risk management, diagnosis, optimization, etc. In the broadest sense, we can use a Bayesian network for decision support. And in this context, you will see our software in action, BayesiaLab. That's the program that we use for machine learning Bayesian networks, for editing them, for performing inference, analyzing, simulating, optimizing, all within the Bayesian networks framework. BayesiaLab itself is actually just one of several modules that are available beyond BayesiaLab Professional that we will see today. We have an academic edition, education packages, an API, a web simulator, plus many other add-on modules that allow you to introduce BayesiaLab into your research workflow. Let me address a few frequently asked questions up front. First of all, The presentation slides that you see, all of them will be available for download. Also, a recording of this webinar will be available later today, so you can watch it again or share the link with your colleagues, etc. So all this will be accessible at any time. Furthermore, everything you see today you can try out yourself. We have BayesiaLab trial versions available, a more restricted, what we call a more restricted demo version, and then a less restricted evaluation version, or rather an unrestricted evaluation version for which you can apply. So, and the latter would be the most appropriate to experiment with today's data. One more thing I'd like to mention, and that is our course program, our 3-day course program, that is. In fact, we have one starting next week in Dubai, the first time we will ever be hosting a seminar or a 3-day course in the Middle East. We still have space available, so if you want to join us in Dubai on short notice, please do so. The next one in the US will be in the middle of March in San Francisco, and so our course program continues with events all around the world. Now, for questions today, I would once again like to encourage you to submit questions via the question panel that you should have somewhere on your screen, or rather a panel that includes a question portion. So please submit your questions there. We will not have time to answer them in real time during the seminar, but we will answer them offline. You will receive an email with our response. Plus, we will post all questions and answers on the user forum, the BayesiaLab user forum, so you can not only see answers to your question, but also to everybody else's questions. I think this will be quite useful for everybody to see. So, all right. Let's get to our main topic of today, predicting injury severity and optimizing triage. Well, there are lots of elements to this topic, and let me just kind of frame it up. I will start off talking about some caveats, then definitions, premises, some of the principal measures we will be using, some of the key challenges, and then we will get into the process as it exists today, and then we will take a look at how that process could potentially be improved using modeling techniques. So, and here I really need to say, this is obviously a medical subject matter, but we are not physicians, so therefore we are not making any statements about, you know, you shouldn't take this as a medical advice or any of that nature. We're using this topic strictly for methodological illustration purposes. I think having a tangible problem that everyone can relate to really makes understanding modeling so much easier, and that's why we always pick one of those, what we think, interesting examples from real life use cases. But again, please don't take this as kind of medical insight of any kind. And also all the numbers that you see, while they are derived from real data set, treat them as if these were purely fictional. So let's start off with some of our definitions. Or rather a key premise here that I don't want to explain further, and I think everybody will immediately be able to understand. The premise is, if you're severely injured, care at a level 1 trauma center rather than at a non-trauma center lowers your risk of death by 25%. So this, I think, is a commonly accepted premise that various research projects have confirmed. So it's critical that patients with a serious injury get to the center that is appropriately qualified to handle these injuries. And the Center for Disease Control does have guidelines as to how patients should be assessed in terms of whether they are severely injured or not. More specifically, there is what is known as an injury severity score, and the threshold for severe injury is a score of 15 or higher. And the CDC recommends that when field triage occurs, when first responders see the patient, the accident victim for the first time, they should make that determination and send the patient to a trauma center if the risk of having an ISS score of 15 or greater is 20% or higher. So that's the decision criterion. Just to give you a little of background, and you will have all of this in the slides. I don't really wish to read through all of that. Really, that is the official and universally recognized definition of severe injury. It's that this ISS score is greater than 15. And if you're interested, you can also look at how this score is computed. It's basically based on a formula that adds up different individual injury scores for different body parts and then computes an overall number that is determined to used to determine whether you're seriously injured or not. Now, here's the challenge. All this may seem fairly straightforward. Getting that right is difficult. And even though we have very advanced medical centers in many parts of the world, it remains an issue that patients are not properly recognized for their injury. So that is what is referred under triage. So somebody is expected to have a lower score, but then ends up having a higher score, but he or she may be at the wrong hospital given the seriousness of the situation. And of course, on the other hand, it's always a bit of a trade-off. Of course, you could simply overestimate all injuries and assume them to be worse than what they are, to be on the safe side. But on the other hand, then you get on the lower end or the opposite end of the spectrum, then you get a lot of people into your trauma centers that are not really seriously injured. So it's the question of how to trade off over triage versus under triage. If you reduce over triage, minimize that, then you risk missing so many people who actually have serious injuries. So let's review the process. Let's see what is happening in the real world, and we will look at this in the context of a vehicle or of vehicle accidents in general. So traditionally, you have an accident, people call 911, at least here in the US, speak to an emergency operator, dispatcher, who will then activate first responders, fire department, ambulance, rescue helicopter, police, what have you. And once the first responders arrive at the scene of the accident and encounter the patient and examine him, then they determine where this patient should go, whether the patient should go to a trauma center or to a hospital. And again, they use this ISS score of 15 to determine that. The CDC has also issued specific guidelines of how to establish this, or rather how to arrive at that decision. And that includes assessing vital signs. And this is really in order of priority. Assess vital signs, assess anatomy of injury, assess mechanism of injury, and potentially what caused the injury, and then finally assessing special patient or system considerations. So now clearly the first two, vital signs and assessing the anatomy of an injury, that needs to be done by a paramedic, a nurse, a physician, but one could hypothesize that perhaps the mechanism of the injury or evidence of a high energy impact, that could come directly from the car, because after all, your car triggers the airbags and whatever else in active and passive safety systems. So perhaps we could take information not just from the first responder, but rather from the car itself. And this is where automatic collision notification comes in. It has been on the market now for almost 20 years, and I think the results have been very, very positive in general. But now what has more recently emerged in terms of capabilities is that the car could transmit additional accident information. And now this leads to the question, with that additional information that comes from the car, could perhaps triage decisions be made earlier? So instead of waiting for the first responders, could perhaps decisions be made earlier, or could, if you will, the car self-triage, say, hey, this is what happened here, this is what the victims look like and how they are injured. We don't want to take it quite as far. Our question for today is, can crash data improve triage performance? And the way to figure this out is we will develop a predictive model from actual crash data and evaluate how well this model performs. And for that, we're going to use the National Automotive Sampling System. And this is really a great database because for several decades now, I think this goes back into the 1970s, the US government, more specifically NHTSA, has collected systematically crashes from around the country and recorded many, many aspects from these crashes, literally hundreds of variables per crash. And that is what we're going to use today. We're going to look at actually a specific subset of that data. We're just going to look at 2 vehicle collisions that were recorded between 1995 and 2011. We are looking at just passenger cars and light trucks, model year 1995 or later, and we're also only going to focus on the driver. So we're not looking at any of the other occupants. And we're reducing this problem just for expository simplicity. We just want to really to focus on the principal question and not get sidetracked on so many other related questions, obviously. Out of all the hundreds of variables, we're taking 39 variables as potential predictors, and our total data set is roughly 22,000 accident records, injury records. So here I have a list of all the variables that are involved, and I'm not going to read through all of them, but they relate to road conditions, lighting conditions, of course, collision data, how the vehicle collided, where it collided, the angles, the speeds, and so on. Plus, it includes the accident data about the accident, victim, age, height, weight. Of course, the many details about the injuries themselves. But what we are principally interested in is here the injury severity score that is recorded in this database. So that's what we're trying to model based on all these variables that we have here. Okay, so much for the introduction. I think I'm within my 20-minute limit for the intro. Let's get to the practical part. And here are the steps that we're now going to take. We start off by importing this data set. We will perform discretization. We will use dictionaries for handling metadata. We will do some exploratory analysis. And once we kind of have done a sanity check on our data and are convinced that it represents this domain correctly, then we go into predictive modeling, where we will go through several cycles of supervised learning, performance analysis, and repeat this several times until we're satisfied with the quality of the model, with the ultimate objective of trying to answer, is this a useful model for our purposes? Can we adequately predict the injury score? Can this be used in the context of triage? Now, all the data that is contained in the National Automotive Sampling System is in SAS format. And as you may know, SAS has a lot of metadata as part of their files, value labels, long variable names, and so on. And sometimes when you export that raw data from SAS, you may lose some of that. Now, luckily, there are two software packages that in conjunction can retain all that information and make it very easy to import the original SAS data with all its details, with all its metadata and labels into BayesiaLab. And the two software packages that work in conjunction here are Stat Transfer 14 and SAS Decoder. They work hand in hand to make this process very, very easy. Okay, so much for PowerPoint for now. Let me leave that and let me switch to and bring up, yes, so here we're now in BayesiaLab. And yeah, now we want to proceed with our data. We want to import our data. I go to the file named ISS. That's my raw data file. It is in a simple CSV format. And now my GoToWebinar panel is obscuring part of my screen. Hopefully you won't see that, but it's kind of blocking my view here. So perhaps I can just bear with me as I'm moving that to the side. So here's the first step of our data import wizard. We can see all the variables that we have, all 39. In fact, I think we have 40 because we also have a weight variable that we will use for weighting our purposes. NHTSA has weighted the data so it is representative of the actual number of accidents that have happened. So now I'm in step 2 of our data import wizard. Here I have the ability to assign this first weight variable and tell BayesiaLab, yeah, this is the weight. Then we have quite a number of categorical variables. And then towards the end, we have a whole bunch of numerical variables. Here, for occupants, BayesiaLab guesses that this is discrete. I'm overriding that and I'm saying this is continuous. So same thing for events. All right, this is the preview of our data. Let's go to the next step. Here I'm choosing the missing values processing algorithm, but as opposed to last Friday's webinar where we were kind of experimenting with the different missing values processing algorithms, here we leave it at the default using the structural EM. That is always a safe bet. And given that we have a relatively small amount of missing values of only around a little over 1%, we can easily handle that. There's not too much of a computing resource penalty for doing it that way. All right, next step. This is very important because now we need to discretize all of our continuous variables. So, and there I would ask you to watch closely because this is a very, very common approach that we are taking. And so you may want to, really watch this because I'm taking a two-step process for discretizing these numerical variables. First, I will discretize the variable ISS, which will be our target variable. I will first discretize that separately. So I am bringing up the manual discretization for ISS and click on density function that gives me the distribution of this variable. I forgot to mention that the overall range of the value range for ISS is from 0 to 75. 75 is the most severe condition. This means it's you have a fatal injury. And luckily here in our data set, the modal value is 0, and we have only a relatively small number of very, very serious injuries. But in our context, we are only interested in really under versus over 15. That's the criterion that is universally used. So I'm directly entering this here into our panel, and you now see a vertical bar that delineates my distribution, and we can see that we have roughly 99% of observations to the left and a little under 1% to the right of that distribution. Okay. Now, next is I want to discretize all my other variables with regard to this binning. So I want to make sure that the other variables are discretized in such a way that I have the maximum information gain with regard to the target node ISS. The way I do it, I first select continuous and then control click on ISS, thereby deselecting it. So now I have highlighted all my other continuous variables with the exception of ISS, which I have already manually discretized. Now I proceed to selecting the discretization algorithm. And here, given that I have ISS already discretized, I can choose that as a target variable and employ a tree discretization algorithm. So I've selected tree, and with tree, I can choose target. Now, there are many categorical variables that could be a target. Any categorical variable could be a target, but we are obviously interested in ISS, so I'll make that the target. I select 3 intervals. I've experimented with this a little bit earlier and came to the conclusion that's a good number of intervals, and then click finish. Now, BayesiaLab is trying to discretize all the continuous variables on that basis, but now it says, hold on, I can't do that for the variable rollover. So it prompts me to select an alternative discretization algorithm. I select perturb tree and says, if you encounter another such situation, do the same thing again. Okay, it proceeds. And now it says, you know what, that doesn't work either for rollover. So what's your third choice? And now I'm selecting the R-squared genetic optimization algorithm, which is a very safe bet. That should, well, actually, I spoke too soon. No, it's not working. Later on, we can look at why the distribution can't be easily discretized. So I'm defaulting to density approximation. That should definitely work. Okay, and it does. So I've basically gone down my list of priorities in which way I would like to discretize my variable. But it appears only rollover was a troublemaker in that regard. So, all right. And here is my data set, or rather my nodes that now reflect the underlying variables and all the associated data. So now some of these variable names are a bit cryptic. This has reasons of, database legacy, because sometime in the distant past, variable names were limited in length. And so many databases that have lived for a long time are still sticking to this concept. So I will add longer variable comments, and I'll do this via dictionaries. Dictionaries are the way we can handle metadata with BayesiaLab. And you can see there are several menus that allow us to record all kinds of metadata, everything from node colors to discretization, images, and so on. Today we'll only use a few of them, but let's start here with node comments. I have previously created a file that associates long variable names to these short cryptic names. And let me also change the layout a little bit so this will be easier to read. I've selected a staggered layout, so now when I turn on the long variable names, they don't all overlap. So now you can see what each variable really means. But for now, I'll turn it off. Later on, as we interpret the model, can certainly turn that back on again. Okay, so we could now immediately proceed to supervised learning and build a predictive model, but I want to do a little bit of due diligence here to make sure we get a sense of what is contained in this data set and whether all of this is plausible. We may want to check some individual relationships, whether they are of the correct sign, and so on. So I will start with unsupervised learning, and for that purpose, I will employ the Soplec learning algorithm. But given that we have a very large data set, I will increase my structural coefficient in order to kind of keep the complexity manageable and also to manage the learning time. So I've set the structural coefficient to 2, and now I go into unsupervised learning and select Soplec. And now you should see how the Bayesian network grows, how BayesiaLab is adding and deleting arcs to see whether this MDL score can be improved. At the very bottom of the screen, you see that score being shown. And this is something we talked about, I think, in the first webinar 2 weeks ago, how BayesiaLab in all its search algorithms is trying to minimize that particular score. So I think it found the best possible score and has re-estimated the missing values. And now we have something that looks like a pretty big mess where we have just lots of arcs and nodes. And I would argue that this is quite difficult to interpret. Let's use our automatic layout algorithm. Here we go, shortcut P. That's always perhaps the most important shortcut there is in BayesiaLab. I can apply that repeatedly and try to find a layout that is pleasing to the eye and, you know, easily understandable. But I think here we're not having much luck at all because, yeah, this isn't becoming any clearer, at least not in 2 dimensions. So I'm going to switch into our mapping view, which hopefully helps us to understand this a little bit better. I go to Analysis, Visual, Overall, Mapping, and then I select 3D Mapping. This is now bringing up the network again, initially in 2 dimensions, but when I now click P for the automatic layout, it stretches this network into 3 dimensions. And now you can see how I'm turning it, and you can see that this has depth. Now, we could just look at the structure, or more importantly, I will select node force and apply that as a measure to be visualized on the nodes. And then secondly, I'm going to apply Pearson correlation to the arcs, because that's the most easy, or the most easily interpreted measure. So, and okay, let's just move this around a little bit and explore that. All right, here it seems like to the front in the right, the ones kind of closest to the viewer, these are all accident measures, like such as the longitudinal component of the speed delta, uh, or manner of collision, pre-impact stability, airbag deployment, etc. Then here to the left, what I'm now bringing to the foreground, here we seem to have vehicle-related variables such as footprint, weight code, track width, curb weight, wheelbase, model year. And then as I turn it around, we can go to the back. And here you see a triangular relationship. Here we have occupant's sex, height of occupant, occupant's weight, and so on. So this all seems fairly plausible because we know height is related to weight, is related to gender, and so on. So I don't want to spend any more time now, but in general, the way these variables relate to each other seem plausible, and certainly any domain expert could look at this and say, yeah, this makes sense, or hey, there's something really weird because we have variables that are, that make no sense. But I will accept it for now and leave it as is. Okay, now let's move towards supervised learning, and I'll quickly bring this network back into its original condition, or rather remove all arcs and change the layout to the original staggered layout. So now we have a very clear view again of all of our variables. And now, as we work our way towards supervised learning, I will need to set aside a test set, because this is what we're going to, or rather the test set we will need to ultimately perform a performance analysis and see how well this network does. I will create a test split, and here given that we have so much data, I will use a relatively generously sized test set of about 40%. So now that is set aside, there is this teeny tiny icon in the lower right-hand corner that tells me that now I have a learning and test set split. And at any point, I can later on remove that again. But for now, I obviously keep it for performance assessment purposes. I also must not forget to return my structural coefficient to the original default level of 1. Okay, now one might be tempted to move forward with learning, but we need to remember we've just set aside a test set, whereas our discretization was performed on the entire data set. So that would be cheating. It's a mistake that happens quite often, and in fact, in last week's seminar, I did exactly that mistake, so I don't want to repeat that. And now rediscretize all our continuous variables with regard to the target node ISS. I'm using exactly the same process. Now I'm prompting this manually as opposed to what I previously did during the data import. So I will select the tree discretization algorithm, use ISS as the target, 3 bins, and I'll go through the same steps again. Have rollover, have a hang up again with rollover. Oh, okay, hold on, R squared gen opt. Let's see. Okay, we're about done. All right. Here I get my discretization report. We didn't see that earlier. It just gives us a quick summary of how my variables, my continuous variables, were discretized. I'll close that. And now, I think now we're about ready for learning. I will make ISS my target node. I just held the T key and then double clicked on it. Alternatively, I can also have set that via the contextual menu here. Okay, all right, I think we're now good for learning. I go into the learning menu, supervised learning, and I will select augmented Markov blanket. That's perhaps the most universal learning algorithm that we have. Let me start that. Okay, here's our first model. We have now a selection of variables that BayesiaLab found. Let me change the layout here so we can focus on just those variables. Let me stretch this out so we can see what's going on here. Okay, what was selected? And perhaps this would be a good time to turn on our labels. We have age of occupant, lateral component of delta V. This reflects the side impact, longitudinal component, Glasgow Coma Scale score, number of recorded events in accident. That refers to how many individual elements there were in the accident. Let's say you were first hit from the rear and then somebody else hit you from the side and then you rolled over. So that would be 3 individual events that are part of this accident. Then we have a variable that represents entrapment. And I think, and then of course at the center here, injury severity score. And now I forgot, I'm not sure, I've mentioned age of the occupant already. So those are part of our network. And now the first thing that dawns on me is, well, Glasgow Coma Scale score, we can't really use that as a predictor because, you know, that's almost like a proxy. That is a score that tells you how alert you are. It's a scale from 0 to 6 or 1 to 6, with 6 being you're fully normal and alert, and 0 meaning that you're unconscious and don't respond to anything, or worse even. So that makes no sense to include that because that variable we obviously could not observe at the time the car transmits data to the dispatcher. So let's throw that out straight away and exclude that variable. Oops, I didn't want to exclude the target node. So let's learn it again. This is a very typical process that you learn a model, you realize, well, that one is not available. Let's learn it again and see whether now that variable is missing, perhaps something else pops up that we can use. And indeed, let's rearrange the layout again. And let me just stretch this out a little bit further. Another variable came into play, and that is let me bring all of them up. That's the manual belt system used. This is basically an indicator whether the driver wore the seatbelt or not. Okay, this looks better, but gee, there is another one that we can measure, and that is entrapment. So let's kick that one out and relearn our model. Okay, now BayesiaLab chooses not to include anything else. Later, as we fine-tune the model, we will certainly explore further whether we can include perhaps other variables that may be helpful. Now, what about age of the occupant? Now, that's sort of in between. While the car certainly can't guess how old the driver is and transmit that, but perhaps in the records of the telematics services company, they perhaps know the age of the driver, or perhaps we can infer the age from some other variables. Let's say perhaps we have an accident that happens at 2 a.m. on a Saturday night. That would probably suggest that the person who's driving is younger rather than older. and so on. So let's perhaps leave that in there, but declare it as unobservable. And in BayesiaLab, we handle this via the cost with the cost property. So that means it's the variable is part of the network, but as we evaluate the network, we're not setting evidence on it, so it's not contributing directly to the predictive performance. Okay. Now, before we proceed in assessing the model's quality, I just want to look at in a little bit more detail at the longitudinal component of delta V and the lateral component of delta V. I think these are really interesting variables because they keep popping up very, very consistently. So just want to examine, well, how do they relate to the injury severity score? Let me run that. I will just run a target mean analysis that will perhaps give me a sense of, you know, what's happening, what do these variables mean? Okay, interesting. So you see now two curves on this plot, a green one and then a pink one, and the pink one is kind of V-shaped. And the way to interpret this is on the x-axis we have the delta V in miles per hour, so the speed difference that occurred through the accident. So perhaps, and I should probably annotate the screen here. Let me see whether I can use the spotlight here. So at this point, minus 40 means that the crash brought about a speed change of minus 40 miles. So your car decelerated by 40 miles an hour. So that's a pretty strong impact, and therefore the mean injury severity score is the highest for that. So this is a full blast frontal impact. As the speed difference decreases, the injury severity declines. So, and then perhaps more interesting is the lateral component. So the way the coordinate system is set up, that positive x is in the driving direction and positive y is to the right from the driving direction, so at a 90-degree angle. So which implies this is a speed delta that implies a crash and impact from the right. So here a vehicle is hitting you from the right with a speed delta of minus 25 miles per hour. And then as that speed delta goes down, the injury risk goes down. But then it goes up significantly all the way here to the maximum level in this plot. And this is when another car hits you from the side with a significant speed difference. This is when the driver gets hit in the driver's door. So this is how we can interpret that. And hold on, I need to turn off my highlighter again. So this is another step we should take, kind of a sanity check. You know, are these relationships interpretable? Are they useful? Are they in sync with our domain knowledge? Okay, now perhaps we can, with the model as we have it, let's run a performance analysis. Let's see how well these predictors that are included in the model do predict our target node. So let me run that. And please note, I'm now selecting multiple thresholds to be evaluated. This will become very important as we proceed. So, okay. Oh, hold on. I forgot one thing. I need to declare my target state as greater than 15. That's what we're interested in. So we want that to be evaluated in our performance analysis. Okay, so There's now lots to see in this report, and we don't have time to go into all aspects. Perhaps the starting point should be, and I'll try to highlight that again, if I can find my the little icon for the spotlight here. This is the measure that we will keep tracking and evaluating as we look through different iterations of our models. That is what we want to improve. That is the relative Gini index. We don't have time to go through the formal definition that you can find in the Bayesian library on our website, where you get the formulas for all these measures in great detail. So I usually like to start with looking at the ROC curve. This is very helpful because it quickly gives you a sense of what is the classification performance of the model, and furthermore it helps me determine the acceptance threshold, what level I should choose for, or kind of as I trade off true positives and false positives. So that is obviously a key question in all modeling. So I'm going up and down this ROC curve, and BayesiaLab shows me the corresponding level of true positive versus false positive rate and the threshold. So let's say here at this level I have, let's say, let's perhaps use this one. I don't know what's a good number. Let's just randomly pick one. Here we're roughly at 75% true positive rate, 12% so sorry, let me say this again. 75 true positive and 12% false positive at an acceptance threshold of around 1%. So let me enter that here. Now that is obviously a very low acceptance threshold. And I can now look at the confusion matrix and see what that actually means. So at a 1% acceptance threshold, I would have a 71% sensitivity with a 91% specificity. So sounds pretty good in most modeling approaches. This would be quite good. Actually, this is the value I wanted to set. What I've read from the ROC curve. Okay, so 76% sensitivity, 83% specificity. So far, so good. But let's perhaps try and improve this model a little bit further. And the first thing that comes to my mind here is that, we have very few observations for high injury levels. So less than 1% of all of our observations correspond to an ISS score of 15 or higher. So perhaps that is limiting our model. And for that purpose, I'm going to stratify my target node here. I'll kind of upsample my target node to get more observations for ISS 15 or higher, and then see whether that helps us learn a better model. It will not affect the parameter estimation or anything. It will just focus our learning and perhaps help find a structure that can better predict our target variable. So I go to stratification. And this is now very sensitive. I want to be very cautious and increasing the probability here. Let's try that with 2%. So we've increased it from 0.8% to 2%. And with that, you can now see that BayesiaLab indicates the stratification here on our target node as well as in the bottom right corner of the screen. Now we will relearn, perform supervised learning again, learn the augmented Markov blanket, And indeed, we find more structure. So let me zoom out so we can see some of that. Do the automatic layout again. And okay, and we have the same situation as before, because now we brought in a variable, ejection, that we can't really measure, or I speculate that the car currently cannot detect whether somebody was ejected. So that's probably not a good variable to include. However, the other one that came in, I think seatbelt, no, hold on, this one came in, manner of collision, or this refers to, manner of collision means whether it was a side swipe, frontal collision, and so on. So I think we have how many different states? Let me just open up the node editor so you can see. Oops. Oh, I forgot to associate our state names. Let me correct that error. I meant to associate a dictionary with detailed state names that give us correct names for the codes. So now that I've done that, here we see what all these codes mean. So code 1 means rear end collisions, code 2 head on, and so on. Okay. Now I would argue again, the car probably cannot determine this itself, what kind of accident just happened, but perhaps it can be inferred from some of the other things that are observable. So I will treat manner of collision the same way as we treated age earlier on. I'll make that a non-observable node. Perhaps try this one more time. See whether we're missing out on anything. Okay, that's it. And in practice, you would obviously try this for longer and now look at different aspects of your model, structural coefficient, discretization, to see whether you can improve that further. But let's now look at and see whether we actually improve this model by including more variables as a result of the stratification. And now we have a Gini index of 75%. Now, unfortunately, I didn't write down what the number was. It seems like it hasn't changed much. I think it was around, perhaps it was even a little bit higher. I should have written down a note. I'm afraid I can't remember the exact value. Let's look again at a reasonable threshold. I'm just now picking perhaps 2% as the acceptance threshold, or perhaps go a little bit lower. Yeah, actually, it doesn't seem to improve my model at all. I'm still at kind of stuck with a 71% sensitivity, and that obviously I would want to get higher in order to catch all the people who are injured. So, but that's not really the problem here. So in general, I would argue we could now play with this model, get these values up, and perhaps get both sensitivity and specificity to an 85, perhaps even a 90% level. But that isn't remotely good enough for the application we have in mind. Why? Because this ROC curve looks really good. You know, the measures that the ROC index, the Gini index, they are all quite plausible. But here is where everything falls apart, because now I'm going to, hold on. This is what I want to show. This is the problem. This is now a plot of the target state precision and the target state reliability as a function of the acceptance thresholds. The way we read that is if we start here at the bottom end of the spectrum, here at close to 0, at 0 we have a very high precision, meaning we have a very high sensitivity. At a low acceptance threshold, we catch a large amount of the truly seriously injured patients. But the problem is that our reliability is low. So of those whom we have detected, whom we have predicted, most of them are actually not seriously injured. So that's the problem. So if we lower that, if we increase the acceptance threshold to raise the reliability, our performance, our sensitivity goes down. So here we're indeed very far away from the target values that the medical community is aiming for. They are looking for keeping under triage under 5% and minimizing over triage to under 35 or 30%. So here we are very, very far away from that. And this model could indeed not be used for triage purposes. The human touch, the paramedic, the physician still has to look at the patient in order to get a sense, to establish, to create a forecast as to what the injury severity truly is. That is not to say there is not something to gain from this model. What we saw earlier, and we will see this again as we are running here our tornado diagram, there are indeed variables that are meaningful, that indicate in a certain way that the injury risk goes up. In particular, the latitude, the speed difference in the latitudinal direction, that has a big impact, as well as obviously the speed of the frontal impact and so on. So these variables are informative, but not nearly informative in terms of deciding whether or not somebody should be categorized as severely injured. Let me just illustrate this here by setting evidence on the variable dvlat. I'm turning on the full company name, not the company name, the full variable name. And now I'm setting that to the highest level, to the highest bin. And doing so increases the risk of severe injury, or increases the probability of severe injury from below 0.8% to almost 7%. So we have like a 7-fold increase, but still the overall risk of injury severity is below 7%. So there's still a 93% probability that an individual is not severely injured. So we get information from these variables, especially from the speed difference laterally and longitudinally, but not nearly enough to really make a classification decision. With that somewhat disappointing result, but I think it's important to report what we can find, and also kind of temper some of the ambitions that we have with machine learning, where we think, we just throw artificial intelligence at it and therefore can discover all kinds of things. Sometimes we need to realize there are things that we cannot predict with the things that are measurable. And I think this is one of the cases here. So let me conclude. If you're interested in BayesiaLab, please visit our website. We have all details about licensing options. We have details about all the different configurations that you can, in which you can license BayesiaLab. And as I said earlier, you can find answers to all the questions you have just submitted on our website. We will also respond to you directly. One strong encouragement I'd like to share with you, and that is we have our BayesiaLab course in San Francisco. We have several seats still available. So if you're interested, please talk to us. We'd really like you to come. Great location, great venue. I'm sure you would enjoy it. The co-founder of Bayesian, Dr. Lionel Jouve, will fly in from France to teach this course. Later this year, we will have our annual conference in Chicago. We don't have the agenda yet, but we have already several folks who are committed and have confirmed that they will speak at the event. Please join us, put it in your calendar. It would be great to see you in Chicago in November. With that, I realize I've run over a little bit. I'd like to thank you for your time and interest. Here are all my contact details. Please reach out with any questions. Connect with us on Facebook, Twitter, LinkedIn, etc. And don't forget, same channel next week at Friday, 1 p.m. We will continue our webinar program. In the meantime, thanks again and have a fantastic weekend.